right now. There is a structure in the observable universe stretching 1 billion light years from end to end, and the physics that built everything we know says it shouldn't exist. Subscribe if you want more of the cosmos. This is white space. Settle in. There are moments, usually late at night, when you step outside and look up, and the sheer quantity of what you see becomes briefly overwhelming. Not just stars, the suggestion of something behind the stars, something so vast and so indifferent to your presence that the mind slides off it the way water slides off glass. What you're seeing in that moment is not the universe. It is a narrow, fragile sliver of it. The light that has managed to reach you across distances your nervous system was never designed to process. The actual universe, if that word even applies in the singular, begins precisely where your vision ends. This is a journey to that edge, and beyond it. We will travel through layers of structure that no human eye could ever trace directly. We will ask what, if anything, waits past the last reachable horizon. We will examine the anomalies, the dark flows, the great attractors, the gravitational whispers that seem to originate from somewhere we cannot see. We will follow the nature of light itself, the one messenger connecting us to everything we cannot touch, and trace it from the nuclear furnaces of distant suns to the distorted geometries surrounding the most extreme objects in existence. And we will return, as we always do, to the oldest question: what is all of this really, and how much of it is there? Begin with scale. Not as a number. Numbers alone do not communicate scale. They only pretend to, but as a sequence of transitions, each one dissolving the previous frame of reference entirely. Stand on the surface of the Earth and your horizon extends roughly 5 kilometers in every direction on flat ground. The entire planet on which you stand has a diameter of about 12,700 kilometers. If you were to somehow shrink the Earth to the size of a standard classroom globe, roughly 30 centimeters across, then the moon would be a marble-sized object floating about 9 meters away. The sun at that scale would be a sphere roughly 3 meters in diameter, sitting 330 meters down the road. The nearest star system beyond our own? The Alpha Centauri system, which includes Proxima Centauri, the closest known star to the sun, would be nearly 90,000 kilometers away at that scale. On the map of a classroom globe, the nearest star is more distant than the real moon is from the real Earth. This compression of vast distances into something almost imaginable is useful for a moment, and then it fails. Because beyond Alpha Centauri, the galaxy continues for another 100,000 light years, filled with hundreds of billions of stars arranged in a spiral structure whose arms we can barely trace from within. We are located roughly 26,000 light years from the galactic center, in a relatively sparse region between two major spiral arms. Our neighborhood is ordinary in the best possible way. There is nothing unusual about our position in the Milky Way, except that it happens to be where life arose, which is of course the one thing that matters most to us. The Milky Way is roughly 100,000 light years in diameter, meaning that light traveling at approximately 300,000 kilometers per second takes a full 100,000 years to cross it. If you compressed the entire history of human civilization into a single second, the light crossing our galaxy would still be traveling for the equivalent of 4,000 years. And the Milky Way is not an especially large galaxy. Andromeda, our nearest large neighbor, is somewhat bigger, spanning closer to 220,000 light years. Some elliptical galaxies at the centers of massive clusters contain stars spanning millions of light years embedded in diffuse halos of ancient stars that extend even farther. Beyond the Milky Way, things do not become empty. They become populated in a different way. Our galaxy belongs to a gravitationally bound collection of roughly 60 galaxies called the Local Group. The Local Group is anchored by two large spirals, the Milky Way and Andromeda, and contains a menagerie of smaller companions. The The Triangulum Galaxy, the Large and Small Magellanic Clouds, a collection of dwarf irregular galaxies, dwarf spheroidals, and ultra-faint dwarfs that are barely distinguishable from large globular clusters. The entire local group spans roughly 10 million light-years. The Milky Way and Andromeda are currently approaching each other at roughly 110 kilometers per second and will collide in approximately 4.5 billion years, an event that will reshape both galaxies over hundreds of millions of years into a merged elliptical system that astronomers have informally named Milkomeda. The local group exists within a broader supercluster called Laniakea, whose name, drawn from the Hawaiian language, means immeasurable heaven. Laniakea stretches 500 million light-years across and contains the mass of roughly 100 million billion suns. It was only fully mapped in 2014 by R. Brent Tully and collaborators, who used data on the velocities of thousands of nearby galaxies to trace the gravitational landscape, the watershed, as Tully put it, within which local galaxies flow. Just as rivers on Earth flow toward the sea regardless of their starting point, galaxies within Laniakea flow toward gravitational attractors rather than away from them. The supercluster was defined by this flow pattern, not by any visible boundary, and its discovery reshaped our understanding of our own cosmic address as definitively as the discovery that the Milky Way is a spiral galaxy had done a century before. But Laniakea too is embedded within something larger. The universe, at its largest observable scales, is structured like a foam or a cosmic web, a three-dimensional lattice of filaments and sheets of galaxies surrounding vast empty regions called voids. This structure emerged from quantum fluctuations in the very early universe, tiny variations in energy density that inflation stretched to cosmological scales, and that gravity then amplified over billions of years into the immense architecture we observe today. The voids are not truly empty. They contain rarefied gas, occasional solitary galaxies, and the ghostly traces of dark matter. But compared to the dense knots at the intersections of the filaments, the galaxy clusters that sit at the junctions of the cosmic web like dewdrops at the intersections of a spider's web, the voids are as close to nothing as nature appears to allow. The filaments themselves are the grandest structures in existence. They extend for hundreds of millions, sometimes billions of light years. Some filaments have been observed to contain flows of hot gas connecting neighboring galaxy clusters, protocluster material still streaming along the cosmic web billions of years after the initial density fluctuations that seeded them. Where multiple filaments converge, they form what astronomers call walls, enormous flat sheets of galaxies that look in three-dimensional maps of the cosmos, like the walls of enormous soap bubbles. The Boss Great Wall, identified in 2016 using data from the Baryon Oscillation Spectroscopic Survey, stretches nearly 1 billion light-years from end to end and lies approximately 5 billion light-years from Earth. It is not a single structure in the way a building is a single structure. It is a vast sheet of galaxy clusters and filaments that happen to lie in roughly the same plane, connected by the large-scale flow of matter. The Hercules Corona Borealis Great Wall, detected through analysis of gamma-ray burst distributions, may extend for 10 billion light-years, roughly 1/10 the diameter of the entire observable universe. If that estimate is correct, and it remains actively debated because gamma-ray burst surveys are not the most precise mapping tools, it represents a structure so large that the standard cosmological models struggle to account for it. According to our best theories of how structure forms from the almost perfectly uniform state of the early universe, nothing should be able to grow to such dimensions within the age of the cosmos. The formation of structure requires time, gravity accumulates matter gradually, and the universe simply has not been old enough, according to standard models, to build structures at these scales. The Hercules Corona Borealis Great Wall if its extent is confirmed, may represent a genuine challenge to that framework, or it may represent a limitation of the detection method. The answer is not yet in. So where does the observable universe end? And what does that word observable actually mean? The observable universe is not the whole universe. It is a sphere centered on our position in space, not because we are special, but because we define the observation point, whose radius is set by the farthest distance from which light could have reached us since the Big Bang. The universe is approximately 13.8 billion years old. If space were static, the observable radius would be 13.8 billion light years in every direction, giving a diameter of 27.6 billion light years. But space is not static. The universe has been expanding since its first moments, and it continues to expand today, with distant regions of space moving away from us faster the farther they are. Light emitted from a galaxy very early in cosmic history, in the direction of our position, has been traveling toward us for nearly 13.8 billion years. But during that entire journey, the space through which the light was traveling was also stretching. The galaxy that emitted that light is now today, far beyond where it was when the light departed. By the time we account for the expansion of space, that galaxy now sits approximately 46 billion light years away from us in what cosmologists call comoving distance, the distance that accounts for the expansion of space between then and now. Double that for the full diameter, and you arrive at the commonly cited figure. The observable universe spans roughly 93 billion light years. But there is a further subtlety, one that is often overlooked. The observable universe bounded by light, the region from which electromagnetic radiation has reached us, is not the same as the region that has been able to influence us gravitationally, gravity, like light propagates at the speed of light. But the gravitational horizon and the optical horizon differ because of the way space-time expanded in different epochs. In the very early universe, during the inflationary period, regions of space were separating from each other far faster than light could traverse the distance between them. This means there are regions of the universe that were once in causal contact with our region. They shared the same initial conditions, but have since been carried beyond any possible influence. The surface at which this causal contact was last possible defines what cosmologists call the particle horizon, which is somewhat larger than the Hubble horizon, defined by the recession velocity of light. Everything beyond the particle horizon, approximately 45 to 46 billion light years away, consistent with our previous figure, represents regions that have been effectively isolated from us since the earliest moments of the universe. Everything beyond that boundary is, in principle, inaccessible to us, not because there is a wall or an edge, but because no information from there has had time to reach us. It does not mean nothing exists beyond it. It means we cannot, by definition, observe it. The question of what lies beyond the observable boundary is therefore not a scientific question in the ordinary sense. It is a question about the unobservable, which is precisely what makes it so difficult and so fascinating and so central to some of the deepest arguments in contemporary theoretical physics. Several frameworks have been proposed. Each is intellectually serious. None can currently be tested. And the differences between them are so extreme that choosing among them changes nearly everything we think we know about the nature of reality. The most widely discussed is the inflationary multiverse. In the leading models of cosmic inflation, the period of extraordinarily rapid expansion thought to have occurred in the universe's first tiny fraction of a second, specifically somewhere around 10 to the minus 36 seconds after the Big Bang. Inflation may never fully stop everywhere simultaneously. The quantum field responsible for inflation, called the inflaton field, decays at different rates in different regions. Regions where the decay happens early form bubble universes like ours. Other regions continue to inflate. Within those still inflating regions, new bubble universes form, each one with its own initial conditions set by the specific quantum state at the moment inflation ended in that region. Our observable universe would then be one such bubble, a region that exited inflation 13.8 billion years ago. Other bubbles surround us, separated by still inflating space-time that we could never cross, even in principle, because the intervening space expands faster than light could traverse it. Each bubble universe would have its own physical constants, its own value of the fine structure constant, its own electron mass, its own cosmological constant. Most configurations would not be hospitable to complex chemistry, let alone biology. A universe with a slightly larger cosmological constant would have expanded too rapidly for gravity to gather matter into galaxies. A universe with a slightly smaller strong nuclear force would have prevented protons and neutrons from binding into nuclei. We exist in one of the configurations that permits our existence, not because our configuration is uniquely likely, but because only configurations like ours can produce observers. This is the anthropic principle applied to the multiverse, and it is deeply uncomfortable to many physicists because it seems to transform a question of fundamental physics. Why do the constants have the values they have into a question of selection effects? The physicist Max Tegmark has proposed a more radical classification scheme identifying 4 distinct levels of multiverse. Levelize the region beyond our Hubble horizon within the same space-time regions that exist beyond observation but follow the same physical laws. Level 2 is the inflationary bubble multiverse just described with varying physical constants. Level 3 is the many worlds interpretation of quantum mechanics, in which every quantum event branches the universe into multiple versions, each corresponding to a different measurement outcome. Level UV is the most extreme, the mathematical multiverse in which every mathematically consistent structure has the same ontological status as our physical universe. In Tegmark's framework, the universe is not described by mathematics, it is mathematics, and every self-consistent mathematical structure corresponds to an equally real physical reality somewhere in the full ensemble of existence. This is, technically speaking, not a testable prediction in the traditional sense. The bubbles cannot communicate with one another. We cannot send a probe. We cannot detect the other universes through any currently known mechanism. What makes the inflationary multiverse compelling to many physicists is not direct evidence, but theoretical consistency. It emerges naturally from inflationary models without requiring any additional assumptions. What makes it deeply uncomfortable is that a theory predicting everything in principle may predict nothing in practice. A second hypothesis is far more austere. It proposes that beyond the observable horizon there is simply nothing, not empty space, not another universe, but the complete absence of anything that could even serve as a substrate for existence. Space and time, in this view, do not extend beyond our bubble. Our universe is a finite region of space-time floating in what cannot even properly be called a void, because a void still implies a geometry in which nothing happens. In the absolute nothing hypothesis, the concepts of location and distance cease to apply the moment you cross the horizon. There is no there, not even in an abstract topological sense. This is extraordinarily difficult to think about. Human cognition evolved to navigate environments, and environments require space. Absolute nothing. The genuine negation of geometry itself is not an environment. It is the negation of the concept of environment. Whether that qualifies as a physical hypothesis or as a limit on what physical hypotheses can mean is itself an open and serious question in the philosophy of physics. Stephen Hawking, in collaboration with Thomas Hertog, published what would prove to be his final major contribution to cosmology in 2018, shortly before his death. Drawing on the mathematics of holographic duality, the theoretical framework suggesting that the physics of a volume of space can be fully described by a theory defined on its boundary surface, one dimension lower. The paper proposed a model of cosmic origins in which the universe emerged from a quantum state with no definite beginning in time. In this framework, asking what existed before the Big Bang is as meaningless as asking what lies south of the South Pole. Time itself emerged with the universe. There was no before. But the paper went further, suggesting that the implication of holographic duality for cosmology is that the three dimensions we navigate, the distances between galaxies, the curvature of space-time near massive objects, the passage of time, all of it may be emergent from a more fundamental two-dimensional quantum description. If the holographic principle applies to the universe as a whole, then asking what lies outside the universe may be a category error. The outside would be a mathematical structure operating in fewer dimensions than we experience a structure whose properties we cannot even begin to intuit from within the three-dimensional projection we inhabit. These are not fringe ideas. They are discussed in the leading journals of theoretical physics by some of the most technically accomplished researchers in the field. Their shared limitation is the absence of any empirical test that would distinguish between them. And yet the universe itself may already be offering hints. In 2008, a team led by astrophysicist Alexander Kashlinsky published an analysis of galaxy cluster velocities derived from data collected by the WMAP satellite, the Wilkinson Microwave Anisotropy Probe, which mapped the cosmic microwave background radiation with unprecedented precision. What Kashlinsky's team found was unexpected. A population of galaxy clusters spread across an enormous volume of sky appeared to be drifting in a coherent direction, not randomly as the standard model of cosmology would predict, not following the usual gravitational attractions of no nearby structures, but together as though pulled by something massive and distant, something potentially beyond the observable horizon. This coherent motion became known as dark flow. The standard model expects galaxy cluster velocities to be essentially random on the largest scales, the residual noise of structure formation, with no preferred direction that persists across billions of light years. A systematic drift implies a gravitational source whose mass is comparable to or exceeds the mass of everything in the observable universe combined. Nothing within the observable universe can account for it. If dark flow is real, its source lies beyond the cosmic horizon in a region we will never observe directly, exerting a gravitational influence we detect only through its long-range effect on the motion of matter on our side of the boundary. The subsequent decade produced conflicting analyses. Planck satellite data released in 2013 did not confirm the signal at the same level of significance. Kashlinsky's team responded with refined analysis using improved techniques and maintained that the signal persisted. Other teams found marginal detections or upper limits inconsistent with the claimed magnitude. The question remains unresolved. But the possibility that something beyond our horizon could influence the dynamics of our observable universe changes how we think about the horizon itself. It is not a wall, it is not the edge of existence. It is an information limit. And even information limits can be circumvented by forces that propagate at the speed of causality, forces that were established when the regions in question were still in contact, before inflation drove them apart. Closer to home, though home here means within a few 100 million light years, lies another mystery with a name that manages to be both precisely technical and deeply evocative. The Great Attractor is a gravitational anomaly located approximately 150 to 250 million light years from the Milky Way in the direction of the constellations Centaurus and Norma. Its existence was inferred before it was seen. In the late 1970s and early 1980s, astronomers studying the motions of galaxies across a large volume of the nearby universe began to notice a systematic pattern. Galaxies that should have been moving apart from each other, carried by the expansion of the universe, were instead showing departures from the expected recession velocities, departures suggesting they were all being pulled toward a common point. The Milky Way, the local group, and many galaxies within 100 million light-years were all moving in roughly the same direction toward a concentration of mass that was not visible in optical service. The reason it was not visible was geometrical bad luck of the most frustrating kind. This enormous concentration of mass sat almost directly behind the disk of our own Milky Way, in what astronomers call the zone of avoidance, the strip of sky where the dust and gas in our galaxy's disk absorbs or scatters visible light so thoroughly that optical telescopes can see no farther than a few thousand light-years through the galactic plane. Whatever was pulling us was hidden behind our own home galaxy. Penetrating the zone of avoidance required observing at wavelengths that dust cannot easily block. X-ray observations, which cut through gas and dust as effectively as X-rays cut through soft tissue, began to reveal galaxy clusters in the hidden zone. Radio surveys operating at wavelengths of centimeters to meters mapped galaxies that optical surveys missed entirely. Infrared observations sensitive to the thermal glow of stars, rather than the scattered light that dust blocks, provided another window. Gradually, the obscured structure behind the galactic plane was mapped. What emerged was not a single mysterious object, but a complex concentration of multiple galaxy clusters in an unusually dense region of space. The dominant structure appears to be the Norma cluster. Catalogued as a Bell 3627, a massive concentration of several hundreds of galaxies whose combined gravitational pull is one of the strongest in the nearby universe. Its effect on nearby galaxies is severe enough to produce visible tidal disruption. The gravitational field of the Norma cluster shreds passing galaxies, drawing streamers of gas and stars out of them. The spiral galaxy ES0137-001, moving through the hot gas of the Norma cluster at high speed, has had its interstellar gas stripped away by the ram pressure of the cluster medium, leaving a brilliant blue tail of newly formed stars trailing behind it for hundreds of thousands of light years, a ghost of its former structure, a galaxy being dismantled in real time. But the Norma cluster, substantial as it is, cannot by itself account for the full magnitude of the local group's motion toward the attractor. Current analyses suggest it contributes roughly 40 to 50% of the observed velocity anomaly. The remainder comes from a source even more distant. In 2016, analysis from the SARAS survey and related work confirmed the full extent of a vast concentration of galaxies lying well beyond the Great Attractor region at a distance of roughly 600 million light-years. This is the Shapley supercluster, also called the Shapley concentration, the most massive accumulation of galaxies within several billion light-years of the Milky Way. It contains dozens of rich galaxy clusters, thousands of individual galaxies, and a total mass estimated at tens of thousands of times the mass of the Milky Way itself. Its gravitational influence extends across hundreds of millions of light-years, detectable in the systematic motions of galaxies at distances comparable to the Milky Way's distance from it. The Shapley concentration represents, in the current picture, the dominant gravitational attractor for the entire Laniakea supercluster. The current picture, then, is this: the Milky Way, the local group, and the entire Laniakea supercluster are drifting through a gravitational landscape, shaped by multiple overlapping attractors at different scales and distances. We are not falling into a single drain, but being pulled through a complex gravitational terrain, shaped by structures on scales of hundreds of millions to billions of light-years. Whether this motion has any practical consequence is a question whose answer requires timescales so vast they exceed the age of the universe so far. In the meantime, there is a subtler anomaly in our local cosmic environment, one that has become increasingly important in the ongoing conversation about precision cosmology. The Hubble constant is one of the most important numbers in all of physics. It quantifies the current rate at which the universe is expanding. specifically how fast distant galaxies are receding from us per unit of distance. For decades, the Hubble constant was poorly constrained, with values ranging from 50 to 100 kilometers per second per megaparsec, depending on the measurement technique and the assumptions underlying it. The situation was sometimes described with frustration as cosmology's dirty secret. More recently, two independent families of measurement have converged on values with small error bars, and they disagree with each other at a level that cannot be explained by measurement error alone. The first family of measurements is rooted in the early universe. The cosmic microwave background encodes the state of the universe at recombination, about 380,000 years after the Big Bang, and its precise temperature fluctuations, analyzed using the physics of the early universe, allow the Hubble constant to be inferred. The Planck satellite's analysis of the microwave background gives a Hubble constant of approximately 67 to 68 kilometers per second per megaparsec. The second family of measurements is rooted in the local universe. Type Ia supernovae, the thermonuclear explosions of white dwarf stars that exceed a critical mass, have a well-characterized intrinsic luminosity, making them useful as standard candles across enormous distances. Cepheid variable stars, whose pulsation periods are directly related to their intrinsic luminosity, provide an independent rank on the cosmic distance ladder. Measurements using these local distance indicators consistently return a Hubble constant closer to 73 to 74. The discrepancy, roughly 8 to 10%, is known as the Hubble tension. It has persisted through multiple independent analyses, improved calibrations, and increasingly sophisticated statistical treatments. It is now one of the most actively debated problems in cosmology. One proposed explanation invokes a very large-scale local underdensity, a cosmic void that contains our galaxy and the substantial surrounding volume of space. This void, characterized in detail by Keenan, Barger, and Cowie, and sometimes called the KBC void, is roughly 2 billion light-years in diameter. The Milky Way sits several hundred million light-years from its center. The density of matter inside the void is estimated to be roughly half the cosmic average, a significant departure from the homogeneity that the Standard Model assumes at large scales. In this underdense environment, the local expansion of space would appear faster than the global average, because there is less gravitational braking from nearby matter. Galaxies inside the void are being pulled toward the denser walls surrounding it, adding to their recession velocity as seen from inside. A local measurement of the Hubble constant would therefore come out higher than the global value derived from the microwave background, exactly the discrepancy we observe. A DWIS 2020 analysis calculated that the KBC void could account for roughly an 11% enhancement of the locally measured Hubble constant relative to the global value, which is remarkably consistent with the observed tension. If the KBC void is real and of the claimed scale, its existence poses its own theoretical challenge. The standard cosmological model does not naturally produce underdensities of this size and depth. Something in our current understanding, possibly the equation of state of dark energy, possibly the behavior of dark matter on very large scales, possibly the law of gravity on scales of hundreds of millions of light years, may be incorrect or incomplete. Several modifications to the standard framework have been proposed, including changes to the dark energy model, modifications to the initial conditions of structure formation, and the Mond framework, a modification to Newton's law of gravity at very low accelerations, originally proposed by Mordechai Milgram in the 1980s as an alternative to dark matter. Mond has had notable successes in predicting the rotation curves of disk galaxies without invoking dark matter. But it faces serious difficulties in the context of galaxy clusters and the large-scale structure of the universe. And recent analyses of binary star systems in the Gaia satellite data have placed constraints that some researchers believe effectively rule out the simplest models in the astrophysical regime. The shape of the universe is a question that sits at the intersection of geometry, physics, and observation. It sounds like it should have a simple answer. It does not. Early humans believed the Earth was flat because from any local vantage point it is. The curvature is too gradual to perceive directly at human scales. It took careful observation. Ship's disappearing hull first over the horizon. The circular shadow cast by Earth on the Moon during lunar eclipses, the different stars visible from different latitudes, eventually satellite imagery to establish conclusively that the Earth is a roughly spherical body. Determining the shape of the universe faces a version of the same problem. Scaled up by a factor so large, it approaches the incomprehensible. We cannot step outside the universe to observe it from a greater vantage point. We must infer its geometry entirely from measurements made from within. The relevant question is not shape in the visual sense. The universe does not look like anything from outside, because there is no outside from which to see it, but shape in the mathematical sense of topology and curvature. In general relativity, the geometry of space is not fixed in advance. It is determined by the distribution of matter and energy within it. On the very largest scales, if the universe is homogeneous and isotropic, the same in every direction and at every location, as observation strongly suggests at scales above a few 100 million light years, then the geometry of space must be one of three types. It can be positively curved, like the three-dimensional analog of a sphere's surface. It can be negatively curved, like the three-dimensional analog of a saddle surface. Or it can be flat, obeying the familiar rules of Euclidean geometry. In a positively curved universe, parallel lines converge. Two beams of light sent out in parallel directions would eventually meet, and if you traveled in a straight line far enough, you would eventually return to your starting point. Not because you turned around, but because the geometry of space loops back on itself, just as a straight path along the equator of the Earth returns to its starting point. A positively curved universe is finite in volume but has no boundary. It requires a total energy density above a critical threshold. Specifically, the energy density must exceed the value at which gravitational attraction exactly balances the expansion. Current measurements of the cosmic energy budget, which includes ordinary matter, and dark energy, suggest that the total density is very close to critical, within measurement uncertainty of being exactly critical, which corresponds to flat geometry. A negatively curved universe has the opposite properties. Parallel lines diverge. Space extends infinitely in all directions. No amount of straight line travel brings you back to your starting point. This geometry corresponds to a universe whose energy density falls below the critical value. Observations rule out significant negative curvature. A flat universe, which the data most strongly favor, has Euclidean geometry. Parallel lines stay parallel. The angles of a triangle sum to exactly 180 degrees regardless of the triangle's size. This flatness does not constrain the topology, the global connectivity of space. A flat universe can be infinite, extending without boundary in all directions, or it can be finite with periodic boundary conditions, a geometry in which traveling far enough in one direction brings you back to where you started, like a video game character who walks off the right edge of the screen and reappears on the left. Such a topology, a flat, free torus, would be globally finite but locally indistinguishable from infinite flat space, because the period would be so large that the repetition pattern would not be detectable. If the universe were a free torus with a period smaller than the observable radius, the same galaxies would appear in the sky from multiple directions, displaced by the repeat distance. Searches for such ghost images, the same galaxy cluster appearing in opposite regions of the sky with the right apparent recession velocity. have not yet produced a definitive detection, but the searches are limited by the finite resolution of available surveys and by the fact that galaxy clusters evolve significantly over the billions of years that light takes to traverse a hypothetical period length. The primary tool for measuring cosmic curvature is the cosmic microwave background. The CMB contains tiny temperature fluctuations, variations of about 1 part in 100,000, imprinted by density variations in the early universe. The angular scale at which those fluctuations are largest depends on the geometry of the space through which the photons have traveled on their way to our telescopes. In a flat universe, the largest fluctuations appear at the characteristic angular scale of about 1 degree. The data from the Planck satellite, analyzed through multiple independent pipelines, shows that the universe is flat to within the precision of measurement, though a 2019 reanalysis of the Planck data by a group including Renato Brinkmann and colleagues found a subtle preference for positive curvature that other teams have disputed. The question is not fully settled, but the overwhelming weight of the data currently favors flatness, with the uncertainty corresponding to a curvature radius, if any, that would be vastly larger than the observable universe. All of this structure, all of these scales, all of these geometries, everything we have been describing emerged from a single transition, from a state in which none of these distinctions existed to a state in which they did. The Big Bang is often described as an explosion, and the image is not entirely wrong, but it is deeply misleading. An explosion occurs inside a pre-existing space. Matter expands outward from a central point into surrounding regions that were previously empty. The Big Bang was not that. There was no surrounding space. There was no prior emptiness waiting to be filled. Space itself came into existence along with time and matter and energy in what is better described as the rapid onset of a state, the transition from a quantum gravitational regime to the classical universe we inhabit. Before the Planck time, the first 10 to the minus 43 seconds, the universe was so hot and dense that the distinction between space, time, matter, and energy breaks down entirely. Quantum gravity, a theory we do not yet have, would be needed to describe it. What we can describe begins a fraction of a second later. In the first moments after the Big Bang, the universe was extraordinarily hot and dense, so hot that the 4 fundamental forces of nature may have existed as a single unified interaction. As the universe expanded, it cooled. Cooling permitted forces to separate in a sequence of phase transitions. Gravity first, then the strong nuclear force, then the electro-weak interaction splitting into electromagnetism and the weak nuclear force. Within the first millisecond, quarks and gluons condensed into protons and neutrons. Within the first second, the neutrino background decoupled from the rest of the matter, streaming freely outward, just as photons would do hundreds of thousands of years later. Between roughly 1 second and 3 minutes after the Big Bang, the temperature of the universe had cooled to the point where nuclear physics could operate. Hot enough to allow nuclear reactions, but cool enough for the products to survive rather than being immediately torn apart by high-energy photons. This was the epoch of Big Bang nucleosynthesis. Protons and neutrons combined to form deuterium, heavy hydrogen, which then fused into helium-3 and helium-4. About 25% by mass of the ordinary matter in the universe became helium-4 during these 3 minutes. The remainder stayed as hydrogen. Tiny traces of deuterium, helium-3 and lithium-7 were also produced. The precise abundances of these light elements measured today in old stars and intergalactic gas clouds match the predictions of Big Bang nucleosynthesis with remarkable precision and constitute some of the strongest evidence that the universe passed through the hot, dense state the model describes. The universe was still opaque. For the next 380,000 years, it remained a plasma, a hot soup of ionized hydrogen and helium, free electrons and photons, the photons perpetually scattering off the electrons, unable to travel far in any direction. The universe at this epoch glowed as all hot objects glow, but the glow was trapped within the plasma, diffusing slowly rather than streaming freely. Then, about 380,000 years after the Big Bang, the universe cooled to roughly 3000 degrees Kelvin, the temperature at which electrons and protons could combine to form stable neutral hydrogen atoms without being immediately ripped apart again by thermal radiation. This is the epoch called recombination, despite the fact that protons and electrons were combining for the first time rather than recombining. With the free electrons removed from the plasma, photons suddenly had nothing to scatter off. The universe became transparent. The photons that had been trapped in the plasma for nearly 400,000 years streamed freely outward in all directions. Those photons are still traveling today, stretched by the expansion of space from the visible light and near-infrared of a 3000-degree plasma to the microwave wavelengths we detect with modern telescopes. They constitute the cosmic microwave background, the oldest observable light in the universe, the surface of last scattering, the wall of the past beyond which electromagnetic observation cannot penetrate. The universe is at its most fundamental level an electromagnetic phenomenon, and light, the visible form of electromagnetic radiation, is the primary means by which the universe makes itself known to us. What is light precisely? The answer changed several times in the history of physics, and each change required abandoning an intuition that had seemed obviously correct. Newton in the 17th century believed light consisted of particles, corpuscles, which traveled in straight lines and bounced off mirrors according to the same rules that govern the reflection of billiard balls. This explained reflection well. It also explained refraction tolerably, though the required assumption that light travels faster in denser media turned out to be wrong. The main problem was interference. When two beams of light overlap, they produce dark fringes, regions where the two beams cancel each other out. Particles cannot cancel each other, waves can. Thomas Young's double-slit experiment performed in 1801 settled the debate for the 19th century firmly in favor of waves. When light passes through two closely spaced slits in a barrier, the waves emanating from each slit interfere with each other, producing an alternating pattern of bright and dark bands on a screen behind the barrier. The spacing and spacing of the bands depend on the wavelength of the light. Shorter wavelengths produce more closely spaced fringes. The experiment is beautifully clear and decisive. Only waves produce interference patterns. Light is a wave. James Clerk Maxwell, working in the 1860s, showed what kind of wave. His 4 equations of electromagnetism unified the previously separate theories of electricity and magnetism into a single framework and revealed that a changing electric field generates a magnetic field, and vice versa, a self-perpetuating oscillation that propagates through space. Maxwell calculated the speed of propagation from the known constants of electricity and magnetism and found it equal to the measured speed of light. The conclusion was immediate and revolutionary. Light is an electromagnetic wave. But then in 1905, Albert Einstein, the same year he introduced special relativity, proposed an explanation for the photoelectric effect, the phenomenon by which shining light on a metal surface ejects electrons. The puzzling feature of the photoelectric effect was that the energy of the ejected electrons did not depend on the brightness of the light, only on its frequency. Brighter light ejected more electrons, but not more energetic ones. If light were a continuous wave, brighter light should deliver more energy per electron. The explanation Einstein showed requires treating light as consisting of discrete packets of energy, photons, each carrying an energy proportional to the frequency of the light. A single photon either has enough energy to eject an electron or it does not. The brightness determines how many photons arrive, not the energy of each one. Light is both a wave and a particle. This is not a contradiction to be resolved by picking one or the other. It is a fundamental feature of quantum mechanics. Every entity at the quantum level exhibits both wave-like and particle-like properties, and which aspect is dominant depends on the experimental context. The double-slit experiment, remarkably, shows both aspects simultaneously. When light is sent through two slits and detected on a screen, the interference pattern of waves appears even when the light source is so dim that only one photon passes through at a time. A single photon somehow passes through both slits simultaneously, interfering with itself, and arrives at the screen at a location determined by the wave calculation. Detecting which slit the photon really went through destroys the interference pattern. The act of measurement changes the outcome. This is not a technological limitation, it is a fundamental feature of quantum reality. The full electromagnetic spectrum extends far beyond what our eyes can detect. Radio waves with wavelengths measured in meters or kilometers carry the signals of distant galaxies detected by radio telescopes, including the faint hiss of the cosmic microwave background. Microwaves carry the thermal signature of structures in the early universe. Infrared radiation carries the heat signature of warm objects. Human bodies, dusty star-forming regions, the thermal glow of planets. Ultraviolet radiation strips electrons from atoms in planetary atmospheres and drives chemical reactions in the upper layers of stars. X-rays, penetrating soft matter but absorbed by dense materials, illuminate the interiors of galaxy clusters and the hot plasma surrounding neutron stars and black holes. Gamma rays, the most energetic photons, are produced in nuclear reactions and in the most violent events in the cosmos. Gamma ray bursts merging neutron stars, matter falling into black holes. Our eyes are tuned to the narrow band called visible light for a simple evolutionary reason. It is the band in which the sun delivers most of its energy at Earth's surface. The sun's surface temperature is approximately 5,500 degrees Celsius. Objects at that temperature radiate their peak energy at wavelengths in the yellow-green portion of the visible spectrum. As described by Planck's law of blackbody radiation, our visual system evolved to be maximally sensitive to the peak output of our star. A civilization orbiting a cooler, redder star, a K-dwarf or M-dwarf, would have evolved to see in the near infrared. A civilization orbiting a hot blue star would have evolved eyes sensitive to ultraviolet. The visible light we call visible is not a fundamental category of physics. It is the frequency range that happens to be useful on Earth. The color of an object is ultimately a consequence of the selective absorption and reflection of wavelengths. A leaf appears green because the chlorophyll molecules in its cells absorb red and blue wavelengths efficiently. Those are the photon energies that excite the electronic transitions required for photosynthesis and reflect green wavelengths, which are less useful for the chemistry involved. The energetics of the electron transitions in the molecule determine which wavelengths are absorbed, and those energetics are set by the quantum mechanical structure of the molecule, the spacing of its energy levels, which depends on the arrangement of atoms and the distribution of electrons. Chemistry ultimately is the behavior of electrons in the quantum mechanical landscape of atomic nuclei, and color is the part of that behavior that our visual system can detect. A clear sky appears blue because molecules of nitrogen and oxygen in the atmosphere scatter short wavelengths far more effectively than long ones, a phenomenon called Rayleigh scattering, proportionate to the inverse fourth power of wavelengths, meaning blue light scatters roughly 10 times more than red light. As sunlight enters the atmosphere from one direction, blue photons scatter in all directions, filling the entire sky dome with blue light. Red photons pass through with much less scattering. At sunrise and sunset, when sunlight must traverse a much greater thickness of atmosphere before reaching us. Even red light is partially scattered, leaving the deep oranges and reds of dawn and dusk. Where does light come from? In the case of stars, the answer begins in the core, under conditions of pressure and temperature that no laboratory on Earth has yet reproduced in steady-state form. Inside the core of a star like the Sun, the pressure and temperature are extreme enough to force hydrogen nuclei, single protons, close enough together that the strong nuclear force which binds nucleons at short distances overcomes the electromagnetic repulsion between like charges. The dominant reaction chain in stars of the Sun's mass is the proton-proton chain. Two protons fuse to form a deuterium nucleus, releasing a positron and a neutrino. The deuterium fuses with another proton to form helium-3, releasing a gamma-ray photon. Two helium-3 nuclei fuse to form helium-4, releasing two protons and a large amount of energy. The overall reaction converts 4 protons into one helium-4 nucleus. The mass of the helium-4 nucleus is approximately 0.7% less than the combined mass of the 4 protons that formed it. That deficit of mass is converted to energy. The Sun converts roughly 4 million metric tons of mass into energy every second, releasing the energy as high-energy gamma-ray photons in the dense plasma of the core. Those photons do not escape quickly. The interior of the Sun is opaque, far more opaque than any material on Earth. A photon produced in the core is absorbed by the surrounding plasma within a tiny fraction of a millimeter, re-emitted in a random direction, absorbed again, re-emitted again in a process so inefficient that a photon's random walk from the core to the surface takes, on average, between 100,000 and 170,000 years. By the time the photon escapes the solar surface, the photosphere, it has been absorbed and re-emitted so many times that the original high-energy gamma ray has been converted into many thousands of lower-energy photons, predominantly in the visible and near-infrared. Those photons leave the surface and travel at the speed of light. After approximately 8 minutes and 20 seconds, the ones aimed in Earth's direction arrive. Light interacts with matter in 3 fundamental ways: absorption, reflection, and refraction. Absorption occurs when a photon transfers its energy to an atom or molecule. The electron structure of the atom determines which photon energies can be absorbed. Quantum mechanics constrains electrons to specific energy levels within atoms, and only photons whose energy matches the gap between 2 levels can be absorbed. This selectivity produces the absorption spectra that astronomers use to identify the chemical composition of distant stars and galaxies. When starlight passes through a cloud of cooler gas between the star and the observer, atoms in the gas absorb specific wavelengths, leaving dark lines in the spectrum. The wavelengths of those lines are unique fingerprints of the chemical elements involved: hydrogen, helium, iron, magnesium, calcium, sodium, as distinctive as any fingerprint in a criminal investigation and far more reliable. Reflection preserves the direction of light in a controlled way. At a smooth surface, incoming photons bounce away at an angle equal and opposite to the angle at which they arrived. The law of specular reflection. The physical mechanism involves the photon being absorbed by an atom in the surface and immediately re-emitted. At rough surfaces where irregularities exist at scales comparable to the wavelength of light, the re-emission is in random directions, diffuse reflection, and the surface appears matte rather than mirror-like. The transition between the two regimes depends on the ratio of the surface roughness to the wavelength of light. A surface that appears very smooth to radio waves, with wavelengths of centimeters, may appear extremely rough to ultraviolet photons with wavelengths of nanometers. Refraction occurs when light passes from one medium into another with different optical density. As it crosses the boundary, its speed changes. Light travels slower in glass, water, or any transparent material than in vacuum, and if it arrives at an angle to the boundary, the change in speed causes it to change direction. The relationship between the angles of incidence and refraction is given by Snell's law, and it depends on the ratio of the speeds of light in the two media. The fact that different wavelengths of light travel at slightly different speeds in any given material, the phenomenon of dispersion, means that a prism bends different colors by different amounts, separating white light into its component spectrum. The same phenomenon in water droplets produces rainbows. The relationship between light and gravity is one of the most surprising predictions of general relativity, and its first confirmation in 1919 stands as one of the decisive moments in the history of science. In Newtonian mechanics, gravity is a force between massive bodies. Light, being massless, should in principle not be affected. In practice, early physicists speculated that if light had any effective mass at all, any inertia, it would respond to gravity. But the predicted deflection would be small and calculable from Newton's laws. Albert Einstein, developing the general theory of relativity between 1907 and 1915, reconceived gravity entirely. Gravity is not a force between masses. It is the curvature of space-time produced by the presence of mass and energy. A mass distorts the geometry of space-time around it, the way a bowling ball distorts a stretched rubber membrane. And other objects, including massless photons, move along the straightest possible paths through that curved geometry. The resulting paths are curved, not because any force pushes the photon sideways, but because the space through which it travels is itself curved. Einstein calculated that the deflection of starlight passing close to the Sun would be 1.75 arcseconds, exactly twice the value predicted by a naive Newtonian calculation, because the Newtonian calculation does not account for the curvature of time-only space. Arthur Eddington organized the expeditions to photograph stars near the solar limb during the total solar eclipse of May 29, 1919. The eclipse was total for nearly 7 minutes, an unusually long totality that allowed detailed photographic exposures. The stars selected for measurement were from the Hyades cluster in Taurus, a compact grouping with enough members near the solar disk to provide multiple measurements. Eddington compared the apparent positions of those stars during the eclipse with reference plates taken 6 months earlier, when the Sun had moved to a completely different region of the sky. The deflection was detected and its magnitude matched Einstein's prediction. The announcement, made at a joint meeting of the Royal Society and the Royal Astronomical Society in London in November 1919, electrified the public. Newspapers declared that Newton had been overthrown. Einstein became, almost overnight, the most famous scientist in the world. The theory that gravity curves the paths of light, that massive objects act as lenses for the universe behind them, was no longer speculation, it was fact. When light from a very distant source passes near a massive intermediate object before reaching us, the gravity of that object deflects the light from multiple paths simultaneously. Different rays of light from the same source travel different routes around the intermediate mass, take slightly different times to arrive, and are magnified and distorted in characteristic ways. The result, visible in telescope images, is gravitational lensing, one of the most vivid demonstrations in all of observational astronomy that space-time curvature is real. In the most dramatic cases of near-perfect alignment, the deflected light arrives from all directions around the lensing mass simultaneously, forming a complete luminous ring, the Einstein ring. The first complete Einstein ring, designated MG 1131 plus 0456, was discovered in 1988 using radio telescopes. and subsequent optical and infrared imaging with the Hubble Space Telescope has revealed dozens of rings of exceptional clarity. Each one is a direct image of the warped path of light through curved spacetime, frozen in a moment of cosmic alignment. When the alignment is imperfect, gravitational lensing produces multiple images of the background source, whose positions and brightnesses depend on the mass distribution of the lens. In the case of a compact galaxy lensing a background quasar, 4 images of the quasar commonly appear arranged around the lensing galaxy, one above, one below, one to each side, in a pattern called an Einstein cross. The separation between the images, measured in arcseconds, encodes the mass of the lens. The time delays between the images because light taking different paths arrives at slightly different times, and the variable quasar seen through a gravitational lens pulses at slightly different times in each image. Encode the Hubble constant. Measuring the Hubble constant from gravitational lens time delays is an independent method, and the values obtained are currently more consistent with the local measurements from supernovae than with the CMB-derived value, deepening the Hubble tension. Gravitational lensing has become a fundamental tool of cosmology. Statistical measurements of the subtle, coherent distortions in the shapes of millions of background galaxies called weak gravitational lensing map the distribution of dark matter across the universe. Dark matter does not emit, absorb, or reflect light, but it gravitationally lenses the light from more distant galaxies, imprinting a coherent shear pattern on their apparent shapes. By measuring this shear with precision across thousands of square degrees of sky, surveys like the Dark Energy Survey, HSC, and the upcoming Rubin Observatory Legacy Survey of Space and Time will reconstruct the three-dimensional distribution of dark matter across the observable universe and test cosmological models with unprecedented precision. What light reveals ultimately is not just the positions and compositions of distant objects. It reveals the geometry of the space through which it has traveled. Every photon that reaches a telescope has threaded its way through the gravitational landscape of the entire universe between its source and us, and its trajectory records every curve, every distortion, every concentration of mass it encountered along the way. Reading that record requires the entire apparatus of modern physics, from quantum electrodynamics to general relativity to the statistical mechanics of large-scale structure. But the reading is possible, and it grows more detailed with every generation of instruments. We are a species that evolved in an environment where the relevant spatial scales measured in meters, where the relevant time scales measured in years, and where the relevant forces were those we could feel with our bodies. Our nervous systems are not equipped to generate intuitions about the curvature of the universe, the topology of a four-dimensional manifold, or the behavior of photons near the singularity of a black hole. What we have instead of intuition is mathematics, a kind of formalized pattern recognition that turns out, for reasons that remain somewhat mysterious, to be extraordinarily well matched to the structure of physical reality. Eugene Wigner, in a famous 1960 essay, called this the unreasonable effectiveness of mathematics in the natural sciences. The equation that Maxwell wrote down in the 1860s to describe the rippling of electric and magnetic fields predicted the existence of radio waves years before anyone built a transmitter. The equations that Einstein wrote down in 1915 predicted gravitational waves a century before any instrument was sensitive enough to detect them. Dirac's relativistic quantum theory, written to reconcile special relativity with quantum mechanics, predicted the existence of antimatter before a single antiparticle had ever been observed. Mathematics, it seems, knows things about the physical world that we have not yet looked for. With mathematics, we have mapped the universe from the nuclear reactions in the core of the Sun to the large-scale distribution of matter across billions of light years. We have measured the age of the cosmos to within a fraction of a percent. We have traced the history of the universe back to within a tiny fraction of a second of the Big Bang. We have predicted the cosmic microwave background before it was detected, calculated the abundance of light elements before it was measured, and described the statistical properties of galaxy clustering before the surveys to test those predictions existed. What we have not done is reach the edge of what there is to know. Each answer has opened more questions. The Hubble tension hints that something is wrong with our model of the universe's expansion or with our measurements, or both. The Hercules Corona Borealis Great Wall hints that structure can form at scales current models do not accommodate. The dark flow, if confirmed, hints that something beyond our horizon is pulling the observable universe. The dark matter we can detect only gravitationally, comprising perhaps a quarter of the total energy content of the universe, remains unidentified despite decades of increasingly sensitive searches. The dark energy that causes the accelerating expansion of the universe, comprising perhaps 68% of the total energy content, is parameterized by a single number, the cosmological constant. But we have no deep understanding of why it has the value it does, or whether it is constant at all. Together, dark matter and dark energy constitute more than 95% of the total energy content of the universe, and we do not know what either of them fundamentally is. The universe we can see, the ordinary matter of stars and planets and gas and dust, is a thin layer of familiar physics floating on a vast ocean of unknown physics. We live in a universe that is mostly invisible to us by its nature, not by any limitation of our instruments, and we are only beginning to understand the shape of our own ignorance. There is something deeply, genuinely strange about the fact that this ignorance does not diminish us, it enlarges us. The creatures who first noticed the patterns of stars overhead were trying to navigate and to mark the seasons. The creatures who first noticed that the stars are other suns were trying to understand what they saw. The creatures who determined that the universe is expanding were trying to measure distances. At each step, the universe turned out to be larger, older, stranger, and more intricate than any previous model had suggested. And at each step, the response was not despair, but curiosity. A deepening of the drive to understand that seems to be as fundamental to our nature as language or tool use. We look up at the night sky that reveals almost nothing of what is actually there. The stars visible to the unaided eye number only a few thousand out of the hundreds of billions in our galaxy alone. The galaxies visible in a single exposure from a large telescope number in the thousands. The total in the observable universe is estimated at roughly 2 trillion. The cosmic web of filaments and voids extends for billions of light years in every direction. And beyond it all, at the horizon we can see but not cross, the universe continues into regions that are beyond observation, regions that may be governed by the same laws or by different ones, or by no laws at all in any sense we would recognize. Whatever lies beyond that horizon, the light that has managed to reach us across 13.8 billion years of cosmic history carries within it the record of everything that has happened. Every photon in the cosmic microwave background is an emissary from the moment the universe first became transparent. Every photon from a distant galaxy carries information about the chemistry, the temperature, the age, and the motion of its source. Every distorted arc in a gravitational lens is a record of the mass through which light has passed. The universe writes its history in light, and we are just learning to read it. But light is not the only messenger. In 2015, the LIGO detectors, 2 L-shaped interferometers in Louisiana and Washington state, each with arms 4 kilometers long, registered a signal that lasted a fraction of a second and carried the unmistakable signature of 2 black holes merging. The signal was a gravitational wave, a ripple in the fabric of space-time itself, predicted by Einstein in 1916 and finally detected a full century later. The two black holes involved had masses of approximately 36 and 29 times the mass of the Sun, and their merger released more energy in gravitational waves during the final fraction of a second than all the stars in the observable universe combined radiate as light during that same interval. The entire energy was emitted not as photons, not as neutrinos, but as oscillations in the geometry of space-time, compressions and expansions of space itself, alternating at frequencies similar to audio waves, sweeping outward from the merger site at the speed of light. Gravitational waves are not light. They do not interact with matter electromagnetically. They are not blocked by gas or dust. They pass through the Earth, through you, through everything, with no absorption and essentially no scattering. They carry information about their sources in a completely different language than electromagnetic radiation, a language encoded in the curvature of space-time rather than the oscillation of electric and magnetic fields. In principle, gravitational wave detectors can observe the universe back to the very first instance after the Big Bang, through the wall of the cosmic microwave background that blocks any earlier electromagnetic signal. Primordial gravitational waves produced during cosmic inflation would carry information about the energy scale and dynamics of the inflationary epoch directly, without filtering through 380,000 years of plasma. Detecting them is one of the central goals of next-generation observatories. The detection in 2017 of gravitational waves from a neutron star merger, accompanied by electromagnetic emission across the full spectrum from gamma rays to radio waves, marked the beginning of what astronomers call multi-messenger astronomy, the coordinated study of cosmic events using both gravitational waves and light simultaneously. Where electromagnetic astronomy sees the surface of events, the photons that escape from the outermost, most transparent regions, gravitational wave astronomy sees the interior dynamics. Together, they provide a stereo view of the universe, a depth perception that neither messenger alone can achieve. There are also neutrinos, nearly massless particles produced in nuclear reactions, including those in the solar core and in supernova explosions. Neutrinos interact with matter so weakly that a neutrino produced in the solar core passes through the entire Sun, through the Earth, and continues outward with only a tiny probability of interacting with any nucleus along the way. Approximately 65 billion solar neutrinos pass through each square centimeter of your body every second arriving, passing through, departing entirely without your awareness. Detecting them requires enormous tanks of ultra-pure water or liquid scintillator buried deep underground to shield them from cosmic ray backgrounds, where the rare interaction of a neutrino with an atomic nucleus produces a tiny flash of light detectable by sensitive photomultipliers. Neutrino astronomy is in its infancy compared to electromagnetic astronomy, but it's potentially significant. In 1987, when a massive star exploded in the Large Magellanic Cloud, the supernova designated SN 1987A, 3 independent neutrino detectors around the world registered a burst of roughly 20 neutrinos in a span of about 13 seconds. Those 20 neutrinos carried more energy than the Sun will radiate as light over its entire 10 billion year lifetime. The neutrino burst arrived approximately 3 hours before the light from the explosion, because the neutrinos escape from the collapsing core immediately, while the photons are trapped in the outer layers of the star for hours before they blast free. This 3-hour difference confirmed the theoretical picture of core collapse supernovae with extraordinary precision. The Ice Cube Neutrino Observatory, buried deep in the ice of Antarctica and encompassing a cubic kilometer of instrumented ice, has detected high-energy neutrinos arriving from cosmic sources, directions in the sky that correspond to active galactic nuclei and other high-energy astrophysical objects. Each such neutrino carries information about the processes that accelerated it to such extreme energies. Likely the jets of material ejected by supermassive black holes at velocities approaching the speed of light. Like gravitational waves, high-energy astrophysical neutrinos offer a view of the universe that complements and extends what light alone can provide. The role of dark matter in the story of light and structure deserves its own extended consideration. Dark matter, the term first introduced in a modern cosmological context by Fritz Zwicky in 1933, refers to whatever is responsible for the gravitational effects that cannot be accounted for by visible matter alone. Zwicky noticed that galaxies in the Coma cluster were moving much faster than their collective visible mass should allow. By the 1970s, Vera Rubin and collaborators had measured the rotation curves of individual spiral galaxies and found that stars in the outer regions were orbiting the galactic center far faster than the visible disk mass could sustain, as if the galaxies were embedded in vast, invisible halos of additional mass extending far beyond the visible stellar disk. The evidence for dark matter has since accumulated across an enormous range of scales and observation techniques. Gravitational lensing by galaxy clusters shows more mass than is visible. The cosmic microwave background power spectrum encodes the ratio of ordinary matter to dark matter in its acoustic peaks, yielding consistent estimates across independent methods. The large-scale structure of the universe, the pattern of filaments, voids, and clusters matches the predictions of simulations that include dark matter but not those without it. Everywhere astronomers look, the gravitational evidence for unseen mass is consistent and compelling. What dark matter actually is remains unknown. The leading hypothesis for decades has been the WIMP, weakly interacting massive particle. A hypothetical particle with a mass somewhere in the range of 10 to 1,000 times the proton mass, interacting with ordinary matter only through gravity and the weak nuclear force. WIMPs were predicted to be produced in the correct abundance by the Big Bang and to have survived to the present day, constituting the observed dark matter density. Direct detection experiments, enormous underground tanks of liquid xenon or germanium, searching for the rare kick that a WIMP would deliver to an atomic nucleus, have reached extraordinary sensitivities without detecting a clear signal. The parameter space for the simplest WIMP models is substantially constrained. Other candidates include axions, extremely light particles predicted by an extension to the standard model of particle physics, and primordial black holes formed in the early universe from density fluctuations rather than stellar collapse. None has been definitively confirmed. The identity of dark matter is perhaps the deepest open question at the intersection of particle physics and cosmology. The identity of dark energy is equally mysterious and arguably more consequential. In 1998, two independent teams studying type Ia supernovae at high redshift, the High-Z Supernova Search Team and the Supernova Cosmology Project, discovered something no one had expected. The expansion of the universe is not slowing down due to gravity, it is accelerating. Distant supernovae appeared fainter than they would in a decelerating universe, meaning they were farther away than expected. The simplest explanation is that space is permeated by a form of energy with negative pressure, energy whose effect on the expansion of the universe is repulsive rather than attractive. Einstein had introduced exactly such a term into his equations in 1917, the cosmological constant denoted lambda, as a means of producing a static universe. He later called it his greatest blunder. After Hubble's observations showed that the universe was expanding and no such term was needed, the 1998 discovery reinstated the cosmological constant as a necessary feature of the cosmological model. What the cosmological constant physically represents is deeply unclear. In quantum field theory, the vacuum of space is not empty. Virtual particles continuously appear and disappear, and the energy of these quantum fluctuations contributes to the energy of the vacuum, a vacuum energy density. Calculating this quantum vacuum energy from first principles gives a result that exceeds the observed value of the cosmological constant by a factor of roughly 10 to the power of 120. Perhaps the largest discrepancy between theory and observation in the history of physics. Why the cosmological constant is so small, far smaller than any natural scale in particle physics, is one of the fundamental unsolved problems at the frontier of theoretical physics. Some invoke the anthropic principle. A much larger cosmological constant would have caused the universe to expand so rapidly that galaxies could never have formed. Others hope for a deeper theoretical understanding that makes the small value natural rather than coincidental. The universe, then, consists of roughly 5% ordinary matter. The protons, neutrons, and electrons of atoms, the stuff of stars and planets and people, roughly 27% dark matter of unknown identity, and roughly 68% dark energy of equally unknown nature. We have a detailed, precise, observationally verified model of cosmology in which 95% of the content is unidentified. This is not a failure of the model works with extraordinary precision, but it is a profound statement about the limits of our current understanding. The fate of the universe depends on which of several scenarios turns out to be correct, and the answer hinges on the properties of dark energy. If the cosmological constant remains constant, if the dark energy density does not change as the universe expands, then the current accelerating expansion continues indefinitely. Galaxies beyond our local group recede faster and faster, eventually crossing the Hubble horizon and disappearing from view entirely. Stars burn out one by one over tens to hundreds of billions of years. White dwarfs cool to black dwarfs over trillions of years. Black holes, which consume matter that falls within them and slowly evaporate through the quantum process known as Hawking radiation, eventually radiate away their mass entirely over timescales of googles of years. What remains is a nearly featureless, cold, dark, diffuse cosmos in a state of maximum entropy, heat death, the Big Freeze. If dark energy is not constant but grows stronger over time, a scenario called phantom dark energy, the expansion of the universe accelerates faster and faster, eventually tearing apart first galaxy clusters, then galaxies, then solar systems, then planets, then atoms, in the catastrophic event called the Big Rip. In the most extreme versions of this scenario, everything in the universe is torn apart in a finite time. The intervals between the cosmic rip of structures cascade downward from billions of years to millions, to thousands, to minutes, to fractions of a second, until even atomic nuclei are ripped apart by the expanding space-time itself. If dark energy is not a property of the vacuum, but a dynamic field that could weaken over time, the long-term fate becomes more uncertain. A sufficiently slow dark energy could eventually be overwhelmed by gravity, leading to a recollapse of the universe. The Big Crunch, a mirror image of the Big Bang. Whether a big crunch would be followed by a new expansion, a cosmic bounce, is a question that quantum gravity would need to answer, and we do not yet have that theory. What unifies all of these scenarios is that the universe changes on scales of time so vast that they make the current age of the cosmos, 13.8 billion years, seem brief. The universe is not ancient by the standards of its own possible lifespan. We exist in cosmic time in a brief and unusually hospitable window. After the first generation of stars had manufactured the heavy elements that chemistry requires. But before the last stars have burned out and the cosmos has settled into whatever its final state will be. We live in the spring of the universe's long life, when stars are still numerous and bright, and the structures they illuminate are still close enough to study. There is something worth sitting with in that observation. We are not an afterthought of the universe. We are a consequence of it, built from the carbon forged in ancient stellar cores, from the oxygen liberated by supernovae, from the iron dispersed across the galaxy by the deaths of massive stars over billions of years before our sun was born. The heavy elements in our bodies were manufactured in stellar furnaces at temperatures of hundreds of millions of degrees, scattered across the galaxy by stellar winds and supernova shockwaves, swept up in the cloud of gas and dust that collapsed under its own gravity, 4.6 billion years ago to form the solar system. We are the universe looking at itself. The photons that left a galaxy 10 billion light years away traveled for 10 billion years, passed through our atmosphere, crossed the lens of a telescope and struck a detector. Those photons are completing a journey that began before our sun existed. We are the endpoint of that journey, the agency by which the universe records its own history. The fact that we can do this, that physics permits structures of sufficient complexity to model and understand the very cosmos that gave rise to them, is not obvious. Many configurations of the laws of physics would not permit it. Light is not merely what we see by, it is the medium through which the universe communicates its history to whatever observers are capable of receiving it. It carries the story of the early universe in the microwave background, the story of stellar evolution in the spectra of stars, the story of cosmic structure in the distribution of galaxies, and the story of space-time geometry in the distortions of gravitational lenses. It travels at the maximum speed that causality allows, encoding in its polarization and frequency and direction everything about the conditions at its source. We have built instruments of extraordinary sophistication to receive and decode those messages. Telescopes with mirrors 7, 10, 30 meters across. Interferometric arrays spanning continents. Space observatories above the atmosphere's absorbing layers. Detectors sensitive to single photons, and still the observable universe extends to its 93 billion light-year horizon, and still the region beyond that horizon is beyond our reach, and still the questions that matter most remain open. What we know is immense. What we do not know is greater. And the edge between them is the most interesting place in human thought. The night sky is not the universe, but it is where the questioning begins. And the questioning, pursued far enough, takes us to the edge of everything we can know and asks us, quietly and without any assurance of an answer, what lies beyond.